Hello, Legacy Sabers. Marsh here. So today we're going to talk about describing graphs. You're going to want your foldable today, and then you might want other colors as well as we get into the example section. A bunch of today is going to be a lot of definitions for the first part of this information part of this video. Our essential question today, how can I identify key features on a graph such as extrema, intervals of change, intercepts, continuity, boundedness, and symmetry? So literally we're going to be looking at graphs today and identifying all of the important pieces of that graph. So first I want to talk about intercepts. And you guys have been working with intercepts before. The x-intercept is the point where the graph crosses the x-axis. So if you're looking at an coordinate plane and you put a dot on the x-axis, that is an x-intercept. On the other side, the other axis, we have our y-intercept. And he is also a ordered pair or a point where the graph crosses the y-axis. You guys have seen those before as you are working on them. The next part that I want to talk about is intervals. Now, there are different kinds of intervals. If you think about a social studies class and you're looking at a graph that talks about manufacturing, and one of the questions they ask you is, where does it look like the manufacturing increased? The level of manufacturing increased. You'd be looking for a graph that from left to right looks like it's climbing, right? Looks like it's going up. We are also going to be looking at graphs, but just not in a story context. So a graph is increasing on an interval if the y value increases as the x value increases. Now, this line right here is literally them saying left to right, graph goes up. That is what they're talking about here. Okay? So as I go left to right, aka as x value increases, my y value increases, the y value goes up. Now I got as the graph decreases, we're going to call it decreases, if on the interval the y value decreases as the x value increases. Now again, that means from left to right, graph is going down. So that looks like it would be if I draw a car on that graph, the car would be going down the hill. There is another kind of interval. He doesn't show up very often, but he does at times, called a constant interval. A constant interval is if the y value remains the same as the x value increases. So that would be a flat portion of our graph. They don't show up often, but when they do, we want to be able to identify them as well. Then we have what's known as the extrema. That's this word right here. Extrema are the extremes of the graph. That would mean the hills, the valleys, stuff of that nature. So the extrema, one of them we have is the absolute maximum. Now, the absolute maximum, I just realized I missed a space there. There's supposed to be a space right in the middle. The absolute maximum is the highest point of graph where it changes from increasing, so that would be a graph that looks like this, increasing to decreasing. So it's a hill, okay? Absolute max is the tallest hill. It is the Mount Everest of our graph. He is the tallest mountain in the Himalayas. However, I also want to be identifying the lowest valley. In that case, we would call that an absolute minimum. That is when you are changing from decreasing to increasing. So that's going to look something like this. Change from decreasing, so notice I'm going left to right, I'm going down. Then I'm going to increase. So that is a valley in the graph. Now, I also want to identify all of the hills and all the valleys. Even if they're not the tallest, I still want to talk about them and point them out. So if you find a hill, but it's not the tallest hill, what we're going to call him is a local maximum. So he is a maximum, yes, but he is not the tallest maximum. And then we also have what's known as a local minimum. The local minimum, added a couple of bumps to the M there, is any point that is decreasing to increasing. So as any valley on the graph. Absolute minimums are, in fact, also a local minimum. So if you think about it in a mountain range kind of context, Mount Everest, yes, he is the tallest, but he's also a mountain in that range of mountains. So we need to make sure we identify him that he is, in fact, also a local maximum or a local minimum if you're talking hill or valley. Continuous. Continuous is the easiest key feature of a graph because a graph is continuous if its graph can be drawn with a single stroke of your pencil. So that means if I can start on the left-hand side of the graph and I can draw the entire graph without picking up my pencil, I can say that a graph is continuous. Now, if it's not continuous, we will call our graph what's known as discontinuous. Okay? So if a graph is discontinuous, we will call it saying that is discontinuous. Now, there are other words that people like to call x-intercepts. There's actually 3 other ones that we have. So zeros is one word that you'll hear. Ruts is another word. Solutions is possibly another word. And x-intercepts. Those are all actually meaning where the x value of the graph has a y value that is 0. Every single one of those are the same information. And especially on standardized tests, they like to ask this question, not saying x-intercepts. So sometimes they'll say, here's a graph, where are the roots of this function? In that case, they're literally asking, where are the x-intercepts on this function? Sometimes they'll say, what are the solutions of this function? So those are the kinds of things that we need to be aware of because they do show up. Now, depending on how they ask it, depends on how you have to answer it. So if they are asking you for the zeros or they are asking you for the solutions, we're going to write them as x equals a number. So like x equals 5 or x equals 7 or something along those lines if they are asking for a 0 or a solution. If they ask for a root or root and an x-intercept, we will write them as an ordered pair. So, for example, maybe I have an x-intercept of 5, 0. I would write the root as 5, 0, but for my zeros and solutions, I would say that the answer is x equals 5. Okay? Boundedness is the other kind of new information. There are different kinds of boundedness. And really there's 2, and then there's a fourth one as well. What it means, look at this graph over here on the left. Do you see how there's no time that this graph is getting between or getting out of the 1 and -1? It just kind of bounces and oscillates between those 1 and -1. What we'll call that is we'll call him bounded. He is bounded by 2 horizontal lines such that the graph lies between them. Okay? So he is bounded between this line and this line. He will never cross either of those 2 lines. Then what we have is a graph that I can draw a horizontal line above him and he'll never cross that. So what that will be called is bounded above because I drew the line above the graph. That's why he's called bounded above. If there's a horizontal line such that the graph lies below that line. Kind of backwards in that the graph's below the line, but I like to think of not where is the graph, but where is the line that I drew. I drew the line above. Now, since we have bounded above, we do also have what's known as bounded below. So bounded below means that I can draw a line below the graph such that the graph's going to lie above it. Okay, so right here, there is a line right here that I'm drawing. This graph will never go below that line. It's going to look like it's going to get really close, but it's never actually going to go below it. Then what we have is something that is not bounded. That is a graph that if I draw a line, so if I draw a line right here, notice the graph's going through it, right? It crossed over it. I cannot draw a line above the graph that the graph will never get to. And then I can't draw a line below either because that is going to continually go below as well. Can never get to there as well. Review information that also is considered a key feature. Domain and range, we just talked about domain and range. The domain of a function is all the set of possible x values. And of course, we write this in interval notation. Now remember those interval notation, that is brackets, that is parentheses, that is that kind of information. Range of a function is all the set of possible y values, and it is written in interval notation as well. So again, that is, did we get to that point? Yep, bracket. Did we not? Is it an open dot? We have to put parenthesis there. And then if we see that there's an arrowhead, then we're going to say infinity. Old news, because we have identified even, odd, and neither. That was our very first piece of information this year. Remember, even is symmetric about the y-axis, so that means it folds over the y-axis. Odd is symmetric about the origin, so that is a rotation, or if you want to think of it as a fold over the x, fold over the y. And then we also said that it has neither, which means it doesn't have either of those two symmetries. So let's do an example here. So I got this example, and this is where you might want to have multiple colors because it might be assisting on you. X-intercepts. First thing we need to do is identify where does my graph cross the x-axis. So I have a dot right here, and a dot right here. So I'm going to write those as ordered pairs. So I got one x-intercept at -3, 0. I have another one at 1, 0. And my final one is 5, 0. My y-intercept is right here. That's where I'm crossing the y-axis. So in my case, my y-intercept is 0, 2. So now even remember that is y-axis symmetry. That's definitely, because if I fold it on the y-axis, it's definitely going to work. Odd, I am looking to see if I flip it over the x and flip it over the y, will it line up? And it's close, but this one would actually, it would go from here to here, so it would be a perfect match. So this is a neither. Continuous means that if I start on the left and I draw with my pencil, notice I didn't have to pick up the pencil, right? So I would say, yes, it is definitely a continuous graph. Boundedness. Boundedness means, can I draw a line above it so that it won't go past that? Can I draw a line below it? So if I draw a line above, notice, definitely crossing through, right? Can't draw a line above, so it's not bounded above. Can I draw a line below it? Nope, it's still going to go a little below that. So I'm going to say that this guy is not bounded. Okay. Increasing intervals. This is where color might be helpful. So increasing means that from left to right, it looks like the graph is going up. So notice right here, I'm going to kind of color right here. This is the graph going up, right? It is increasing. It stops increasing right here at -1, right? Or 4 on the y. Now, increasing intervals, you're talking about the x values. You're not talking about the y. Where on the y values are you increasing? Okay, so it's saying what x values are corresponding when you are increasing. So I started on the left. So that means I started at -infinity increasing, right? Because over here on the left is -infinity. So I started at -infinity, and I stopped increasing here at -1. And what I find some students like to do is they like to draw a line vertically so that they can see that they're crossing at -1. We're always going to put parentheses in our intervals for increasing and decreasing because at -1, you're not necessarily increasing and you're not necessarily decreasing. It's kind of like a tip-top point, so we can't say that it's actually increasing at that dot. Now, is there another spot on our graph that's increasing? Well, it looks like from here to the end, it looks like my graph's going up again. So what I'm going to do is I'm going to draw a vertical line here. So I'm sitting at 3, so I'm going to say union. So this is us saying basically the mathematical and, saying and this. So union 3 to positive infinity, because I'm going forever to the right. I will be going up. Now, I also have a decreasing interval. So that would be from here to there, right? So from -1, because that's where I started decreasing, to 3, I was decreasing on my graph. Kind of difficult. We'll keep going through that. Every example, we'll talk through it. Constant intervals, there are no flats on this graph. You know what? I'm going to do some quick erasing here so we can actually see our graph nicer. Absolute max. Is there a tippy top highest point? Well, this guy right here, he is not the highest point on the graph because this is going to keep going forever, right? So actually, there is no absolute maximum. We actually can't identify an absolute maximum. Just like how we cannot identify an absolute minimum because my graph forever goes down. So we're going to say none for the absolute minimum. However, this dot right here, he is a local maximum. He is a hill. He's just not the tallest point in the range. So I'm going to say my absolute maximum is at -1, 4. My absolute minimum, aka this valley down here, is 3, -4. My domain, that is saying from left to right, how far left, how far right. Well, we go forever to the left, right? Because this is going to keep opening up to the left. So I'm going to say we're going to -infinity on the left. On the right, we're going forever to the right. So I'm going to say infinity or positive infinity. Remember, you don't need to put that little plus there. I just write it so that you guys can see it. Range, how far down, how far up? Well, domain, my range, I go forever down, forever up. So I'm going to say -infinity to positive infinity for that. And now I need to identify our y value. Now notice it's saying f of -5. It wants to know what is the y value that corresponds to the x value of -5. So what I'm going to do is over here on -5, the x, I'm going to draw a line. And I want to find where the graph hits that. And I want the y value that corresponds, which in this fact is -5. Whew, lots of information, right? Let's try example number 2. Again, let's find our x-intercepts. So over here, got an x-intercept there, intercept there, intercept there, intercept there. We got 4 of them. So it looks like the first dot is -5, 0. Ooh, this one's not a perfect dot. So we're going to have to do a little bit of estimation. It looks like it might be -1/2, -0.25, -0.75, something like that, right? I'm going to say -1/2. The other guy, he looks to be about 1/2 positive. And then that might be 4 points or 4.75, 4 3/4 for this last dot. 4.5 though, wouldn't be wrong. So as long as you're kind of close, I'll accept it. Just make sure you're not saying like, oh, it's 5.7. Like, you know, be careful. Make sure you're close to what you think it could be. It looks like our y-intercept is 0, 1. That dot. This graph is definitely neither, right? Definitely doesn't have any symmetry. Continuous. Can I draw from left to right without picking up my pencil? Yep, definitely continuous. This guy. Can I draw a line above this graph that will never touch? The graph will never touch. Yep, just did it, right? Can I draw a line below this graph that the graph will never touch? Yep, just did it. Because notice these are not arrows, they're dots. So in our case on this graph, we will say it is bounded. Because it is bounded above and it is also bounded below. You could write bounded above and below. That would be also another acceptable way to write this answer. However, it is bounded is one way too. Increasing intervals. So what I'm going to do is I'm first going to take my graph and I'm going to cut it into pieces here. So notice I change from decreasing to increasing there. I change from increasing to decreasing there. I change from increasing to decreasing here. So I'm first going to mark in my increasing intervals. So it looks like I'm increasing from here to here, and it looks like I'm increasing from here to here. So let's find those x values. Notice I can use now these lines to point out those x values. I'm less tempted to use the y values now since I drew in those lines. I'm going to write, -2 is where I started. I stopped at 0 for that first scribble mark. Union, because I have another one to write. 1, 2, 3, start at 3. And I stopped at 4, 5, 6, 7 is where I stopped right there. Okay. Decreasing is the other two. So it looks like I started at -7, stopped at -2, but then I started decreasing again at 0, and I stopped at 1, 2, 3. So from 0 to 3, I was decreasing. There are no constant intervals again on this graph. I wonder if we'll ever see one. Absolute max. Now be very careful. I'm going to do some erasing here so you guys can see my graph better. There we go. Be very careful. You're going to be very tempted to call this guy an absolute maximum. He's not, because remember the definition that we said earlier in this video. We said an absolute maximum has to change from increasing to decreasing. That is not happening here. There is not the actual hill going on. So this guy, this dot right here, cannot be an absolute max because of that. But there is not a hill that is taller than him. So we're going to say that there is no absolute max. And there's also, though, but there's an absolute minimum right here, this guy, because he is the lowest point on the graph. So I'm going to say my absolute minimum is at 1, 2, 3, -5. Right here, though, is an local maximum because he is a hill nevertheless. So I'm going to write him as 0, 1 for a local maximum. My local minimum, I have another valley right here. He's at -2, -3. And just like we said when we were talking about extrema, we also need to say that the absolute minimum is also a local minimum. Just because he is the lowest valley doesn't mean he's also not just a valley as well. So we need to identify that. My domain. It looks like I started at -7. Notice it's an open dot, so we have to parenthesis that. And then he looks like he stopped at 7, but it's a closed dot, so we're going to bracket that side. I colored it a little too much. I can't see if these dots are closed or not. It looks like I start at -5, bracket, because we have a closed dot there. And it looks like I go all the way up to 7 on the range. So bracket there, because it's closed dot. Notice, this is different than example 2, or example 1, excuse me, because I don't have the x, I am given the y. So they want to know what x corresponds to when the y is 4. So what I'm going to do is on my graph here, I'm going to draw y equals 4. I'm going to draw a line there. And I want to find where the graph hits that. I'm going to find the x value, which in this case is x equals 6 for our answer there. Example number 3. Here's what I want you to do. I want you to pause this video right now. And I want to have you, on your foldable, try this example. That way, you can push play, and then you should be able to see if you got the right answers. Reason why I'm not doing this with example 4 is because example 4 is a little harder. So I want you to try example 3. Okay? Go ahead and try it. So now that you've tried the problem on your own, here are the answers to these particular portions. So I have 3 x-intercepts. I have 1 y-intercept. This is definitely an even graph. It's definitely continuous. It is bounded below. That is because if I draw a line down here, definitely is not going to cross it. There is no absolute max. That is because these arrowheads up here. Their absolute minimum, there are two of them actually, right here and right here. So those are those ordered pairs. There isn't a local max. He's right here. There are two local mins. That's because they are absolute minimums. My domain is negative infinity to infinity. My range is negative 6 to infinity. And what x's have a y value of negative 6? Well, that is my two absolute minimums. I did not do the increasing intervals and decreasing because I want to talk through those again. So the increasing interval, again, I'm going to draw some lines here for when I start and stop that. So it looks like I am increasing from, negative 1.75, and I stopped that at 0. And then I increased again at 1.75, and I did that until positive infinity. Decreasing, started decreasing at negative infinity, because it's left to right, right? I stopped at negative 1.75. And then I started decreasing again at 0. And I stopped at 1.75. No constant interval once more on our graph. Example number 4. Example number 4 definitely is a difficult graph because he's a little different. So first of all, let's identify our x-intercepts. It looks like we have one at 0, 0, and we also have one at 3, 0. Y-intercept, of course, 0, 0. Definitely in either graph, right? No symmetry here. This is our first not continuous graph. So we could write discontinuous. You could also write that it's not continuous. You could just write not or no. Bounded, notice I can draw a line above it, and I will not be able to cross that. But I can't draw a line below, it will cross through. So I'm going to say this graph is bounded above. Increasing interval. I'm going to draw through where there is a change of the graph. Now, notice, this is still increasing the entire way up, right? Just because I jumped doesn't mean it's not still going up, because when I changed, I still went up. So that is not a change from increasing to decreasing. So my increasing interval, I'm going to say I went from negative infinity to negative 2, because that's when I stopped increasing. I started increasing again at negative 1, and I stopped at 2. Decreasing intervals. Now, I am only decreasing once. I started at 2 decreasing. And remember, we're going to the right. So we continue decreasing forevermore to the right. So that would be a positive infinity. Our first constant, look how cute he is. He's only constant between negative 2 and negative 1. Absolute maximum, we do have one. He is right there. He is at 2, 3. We don't have a minimum. This is not a minimum because it does not go from decreasing to increasing. We do have another local max. It's the absolute max. We do not have a local minimum. My domain looks like it's going all the way to the left, all the way to the right. My range, all the way down, but we do stop at 3 there. Now, something to keep in mind with this domain and range, okay? Notice right here. If this open dot would have been, let me do some erasing here so we can kind of draw. If that open dot would have been right here, and then it went, okay? Notice there would have been a hole on the domain. 1 through 2 would not have been available. If that would have been the case, we would have said that our domain is from negative 1 or negative infinity to negative 1 bracket, because it's a closed dot. And then I would have said that I started at 2 parenthesis, because it's an open dot, to infinity. So there would have been that hole there. Oh, that's a positive one. So there would have been a hole there. But being that our graph did not do that, there is a closed dot and an open dot on the same line, then there is no problems with 1 in the domain. Same thing could be wrong with range, because notice there's a big giant hole here on the y's between 1 and 2. I need to make sure that the graph has those y values somewhere. in which it does, right? Right here, the graph has those y values. So there is not a hole in the y. If the graph suddenly would have done a turnaround and we would not have had that, or maybe it just kept shooting up off here and we wouldn't have had this piece, we would have said between 1 and 2 is an issue in the range. That is not the case on this particular graph. Last piece, f of 3. My x value is 3. My y value is 0. I want to thank you for staying through this exceptionally long video. It is so much information to find describing of graphs and all these key features. This is something that sticks the rest of the year and in your longevity of your math career. So being able to identify all these intervals and maxes and mins and all of that business will assist you later. But I want to thank you for taking awesome notes today, and I will see you later, Sabers.